So in this section, section 2.2,
what we're going to start talking about is what that picture should look like. So remember, our whole goal in chapter 2 is trying to build a picture of a data set, because remember, a picture is worth 1,000 words. So a graph is just a picture of our data, basically. So a graph needs to be able to stand by itself without the original data set. So in other words, you should have enough information looking at that graph to tell you what that data set measured and what the data looks like. So you have to have a title on every graph. You have to have labels for both axes if we're talking about a graph with axes. And then whenever it's appropriate, we need a legend, a source, and a date, wherever you can include that. So for qualitative data, we can graph qualitative data using a couple different graphs. So the first one is a circle graph or a pie chart. So a circle graph is divided into sectors that represent categories. So in other words, every category is a piece of the pie. And the size of each sector, or the area of each sector, so in other words, how big each piece is going to be proportional to the frequency of the category. So in other words, if you have more data values in a group, then it's going to get a bigger piece of the pie. So here, for example, we have data that tells us about the number of earned degrees conferred in thousands in 2007, and we want to use a pie chart to organize this data. So we have the associate's degree had 728,000 degrees awarded, bachelor's 1525, and so on. So to do this, what you would do is you would first start out by finding your relative frequency. So find the percentage for each of these degree types. So remember, to find relative frequency, it's just going to be frequency divided by sample size. So that, remember, relative frequency is just frequency over sample size. So for associate's degree in this case, we knew our frequency was 728, and we knew that we asked, so 3,007 people, so our relative frequency was 728 at over 327, which was approximately 0.24. So you do that for all 5 of these degree types, find the relative frequency. So from here, once you have the relative frequency, that just tells you what percentage of the circle is going to be for that slice. It's telling you how big each slice is. So in this case, 51% of our circle is going to be bachelor's degrees. 24% of our circle is associate's degrees. For our purposes, if you ever had to do a circle chart, you would use technology to do this. So I'm not going to get into the math behind how you would figure out exactly where to draw the lines at. If you're doing it by hand, a ballpark estimate is fine. It doesn't have to be perfect. But if I ask you to do a circle chart, it's going to be by hand. The next type of graph that we can use for qualitative data is a bar graph. So a bar graph, the bar represents essentially the frequency or the relative frequency, but normally we use frequencies of the data in each category. And it's only for qualitative data. We have a special type of bar graph that we'll talk about in a second for quantitative data. But just a regular bar graph is only for qualitative data. A side-by-side bar graph, we still are talking about qualitative data, but then we're comparing the same categories for different groups. So for example, maybe I want to have a bar graph that tells me how many males and how many females were each were in each type of math class. So I'm going to have my categories be pre-calculus, statistics, and calculus, for example. And then, so I would have my frequencies over here. So let's say 5, 10, 15, 20. And then what I would do is I would just go in. So let's say 15 males were in a pre-calculus class. And 20 females were in a calculus class, for example. And then 5 females were in stats. And let's say 10 females were in calculus. 5 males in stats. 20 males in calculus, for example. And so then, in this case, we need a legend to tell us which color is which. So red, in this case, we said was males. And then green is females. And so you also have to have a title. So in this case, number of students in math class, for example. So that is a side-by-side bar graph. You're comparing the same categories. In this case, our categories are our math classes. You're comparing your categories amongst different groups of data. So let's build a regular bar graph for the distribution of housing types for students in a statistics class. So what we would do in this case, we would have, so you have to have a axis title. So in this case, type of housing, number of students. So you have to have an axis title. You have to have the axes labeled, so my numbers or frequencies in this case on my vertical axis, the apartment or housing type on the horizontal axis. We've got our bars representing our frequencies, and then we have a title. So you always have to have all of those pieces on your graphs. A time series graph. This is just essentially a line graph for data over time. So time series is just looking at data over time. So here we're still looking at quantitative data, but we're taking it over some period of time. So time is always going to be your horizontal axis. Classic place to see a time series graph, think stock market. So stock prices over time. You usually have the stock price over here on your vertical axis, and then time, so each day, for example, the average stock price, and it's going to look something like that. So that's a time series graph. Another example, the amount of precipitation measured each day for 1 month. So let's look at an example of a time series chart. So here we have a table with the number of cell phone subscribers in millions for the years 98 through 2008. So let's construct a time series chart for these number of cell subscribers. So what we're going to do, we're going to let the horizontal axis represent our years. So your horizontal axis, always time. So whatever your time is, whatever time periods you're looking at, that's your horizontal axis. So year in this case is going to be our horizontal or our x-axis. And then the vertical axis is going to represent the number of subscribers in millions. So that's our y-axis. And so from here, all we do is we plot each data point. So the year and the subscribers in millions, and then connect the dots. And so we end up with a graph that looks like this. And so this graph, so it's nice to be able to look at stuff over time because you can see trends in what's happening. So for example, in this case, we can see that the number of cell phone subscribers from 98 to 2008 went up pretty regularly. In fact, almost linearly, almost perfectly linear. And the last type of graph we're going to talk about in this chapter is a stem and leaf plot. So what a stem and leaf plot is, it's very similar to a histogram. But the problem with the histogram is we lose the original data values. So if you do a histogram in the beginning, you're losing your data values. You get the nice picture of the shape, but you forget those data values. So if you need those data values later, you've lost them. You can't get that from the histogram. So stem and leaf plot, still has our original data values. It's a quick way. Typically, we're going to do a stem and leaf plot. It's just a real quick first way to find what our data is going to look like, to get a rough idea of the shape of the distribution. So what happens is we separate each data value into a stem and a leaf. So the way we do this is whatever our data value is, the very last digit, so the last digit of a data value is a stem. Or sorry, is the leaf. And then everything to the left is the stem. So what you want to do is you want to figure out, okay, all my data values, what's the smallest data value? So in this case, 21 is our smallest. And what's the largest? 45. So what that's going to do, you split it up, so whatever the last data value is, and you want everything to have the same number of decimal places for this also. So if something was, say this was 30.6, then what I'm going to do, everything in the 10th position would be my leaves. And so whatever the most decimal places that you have is, that last digit is going to be your leaf. But in general, most of your data values will probably have the same number of digits. And so that's going to be how you figure out your stem and your leaves. So find your smallest value, find your largest value, and get the smallest and largest stems. So in this case, our smallest stem is 2, our largest stem is 4. You have to include every single stem between those two. I don't care if you have a leaf, so if there's a data value that matches that stem or not, you have to have every single stem. So let's say my largest data value was 80, so I had an outlier here. Then my stem and leaf chart, I'm going to have all of my stems from 2 to 8, whether or not I have data values there. So if I'm using this data set, and let's ignore the 30.6, let's just say it's still 30, then I know I don't have any leaves to go on 5, 6, and 7. Still have to have them. Whether or not there is no leaf for it. And then from there, all you do is you just go through each data point, figure out, okay, where's the stem for this one? And then what's left, the last digit's going to be your leaf. And so you just put it on there. So 21, for example, 25, 25, 26, and so on down. So 27, 28, 30, 36, 36, 45, and then since I added 80, 80. So that would be your stem and leaf plot. Now this is a unordered stem and leaf plot. So unordered stem and leaf plot, and you can put the leaves in either order. So you can have it 7 to 15, or you can have it 15 to 7 from top to bottom. Typically we're just going to go from smallest to largest from top to bottom. So notice here, for example, I have no 8 or no 9. They have no leaves, but they still have to be in your stem and leaf plot. So an unordered stem and leaf plot, the leaves are in any order. They're not in any specific order. For a ordered stem and leaf plot, you just put the leaves in order. That's all you do. So put the leaves in numerical order. You do have to have a key every time, just to say what the stem and what the leaf represents, just so that you can identify the values. And you still need a title, so you still have to have all of that. There's one more type of stem and leaf plot you might see on the homework, which is a split stem and leaf plot. With a split stem and leaf plot, all that is you split each stem into 2 rows. So you have 2 rows for each stem. So the first row only gets leaves of 0 through 4. And the second row, so you're splitting them in the middle. Second row gets leaves 5 to 9. That's it for a split stem and leaf plot. So what stem and leaf plots, what histograms tell us? They give us a picture of the shape of the distribution, which then tells us the kind of math we can do with it later on. So a symmetric distribution, just think of this as a mirror image. So if you draw a line down the middle, you have a mirror image on both sides. Don't worry about this pink stuff talking about mean, median, and mode at the bottom of the image right now. I'm going to come back to this in chapter 3 after we talk about that and talk about what that means based on the shape of the distribution. So for a symmetric distribution, think of it as your classic shape like a bell. So most everything's in the middle, and you have a nice, pretty picture from both sides. It's the exact same, or close to the same. They're going to be roughly mirror images. A uniform distribution is a special symmetric distribution where all of the classes have equal frequencies. So everything is equal, everything is uniform. It's also known as the rectangular distribution. We're not going to talk a whole lot about uniform distributions because in the real world, most things aren't perfectly even. A skewed left distribution. Skewed just means what direction does my data kind of trail off to. So in this case, if it's skewed left, my data, if I draw a rough estimate of a line over it, it kind of trails off here on the left-hand side. So skewed left, then you're going to have a trail off to the left. Don't worry about mean is left of the median. I'll come back to that in chapter 3. Skewed right, the opposite. So in this case, the right tells me my trail, or my tail in this case, is off to the right. So it's trailing off to nothing on the right. And bimodal, look, you're going to be able to tell it because you're going to have 2 humps or more humps. You can have a multimodal one. You're going to have 2 humps, though, for a bimodal. Usually what this means is you're sampling across 2 different populations. So, for example, this might occur with height. So, typically what's going to happen, if you're looking at height, your 2 populations are going to be gender. So this would be females, because females are typically shorter than males, and then males. So that's a bimodal distribution. Alright, so now you have information about this section, these 2 sections. So go do the homework,